So section 7.2 is more confidence intervals. This time, though, it's a little bit more realistic case. We're still estimating the population mean, but this time we do it when sigma is unknown, which is way more likely to be the case. So, thing to notice here, it says in order to use a normal distribution to find confidence intervals for a population mean mu, we need to know the value of sigma, the population standard deviation. Okay, that's what we had in section 7.1. Most of the time, however, when sigma is unknown, when mu is unknown, sigma is unknown as well. So if you don't know the population mean, most likely you're also not going to know the population standard deviation, sigma. In such cases, we use the sample standard deviation, little s, to approximate sigma. So we'll have our sample, right? We have the sample, we had the sample mean that we used in 7.1, but now we're going to also, from our sample, find the sample standard deviation and use that to approximate sigma. When we use little s to approximate sigma, the sampling distribution for x bar follows a new distribution called a student's t distribution, or t distribution. So we've got a brand new distribution today, student's t distribution, and it's kind of got a weird history, but the one who came up with this was, last name is Gossett. And I can't remember his first name, but he worked for Guinness, the maker of beer. And this was, a long time ago, 100 years ago or so. And he was hired at the time. He was a chemist, also a mathematician, and I think he was brought on for quality control. So they wanted to have the beer that was made, they wanted to have some consistency. And so he was brought on board, and they were a little afraid of other breweries copying them, so they had a strict policy against publishing. Well, Gossett had discovered something pretty interesting. At the time, he was thinking it could be used for small samples when you can't use a normal distribution, and he knew that it would be useful in research, in all areas of research. So he really felt strongly that he needed to publish this information, and he also knew that it couldn't directly be used to hurt Guinness. It would just be used in research in a lot of other areas. So he published it with the pseudonym of Student. Why he chose that one, I don't know, but that's where it came from. So Gossett came up with it. The distribution is called Student's T. So here's how we'll use it. So suppose that X has a normal distribution. So we're sampling from, the distribution we're sampling from has a normal distribution, or is at least reasonably mound-shaped and symmetric. It's got a mean mu. For samples of size n with sample mean x bar and sample standard deviation s, the t variable, so instead of a z-score, we're going to get a t-score, but it's really similar to what we've seen before. The difference is here we've got little s instead of sigma, and we've got a t-score instead of a z-score. But otherwise, it's very similar. One thing that is a little different with student's t, though, is we have this new thing called the degrees of freedom. The degrees of freedom is n minus 1. Remember that n is the sample size. So we have this thing called degrees of freedom for student's t, and we'll talk about it a little bit more later, but basically degrees of freedom is going to be n minus 1. So if you have 20 samples and you're using student's t, that means you've got 19 degrees of freedom. And the little note here, this will be very similar to what we've seen before. So the note is, if we cannot assume X has a normal distribution, or is at least reasonably mound-shaped and symmetric. But we'll just say, if we can't assume X is a normal distribution, we need a sample size n greater than or equal to 30. So just like before, we still have our magic number of 30. If we're going to use student's t, well, if we're sampling from a normal distribution, then the sample size doesn't matter. But if we don't know that, if we don't know we're sampling from a normal distribution, so we don't know that X is normal, or maybe we know that it's not normal, well then we are going to need a sample size of 30 or more, just like before. So this will seem a lot like what we did before, except now we've got to find this critical value t sub c, instead of z sub c, t sub c. And this is where we're going to have to use a table for this. So there's a way to do it on the calculator, but not all calculators have it. But even if your calculator does have it, it's actually easier to use a table. So on any test or quiz, I'll give you a student's t table. You have one in your book also. It's right by the standard normal curve. Usually right behind it is the student's t table, or the standard normal table, excuse me. So here's how we do it. So for this one, first thing we have to notice is we've got sample size n equals 10, which means our degrees of freedom, which will be n minus 1, will be 9. So we've got 9 degrees of freedom. So to use the table, we look for t 0.95, and we're going to have to, I'm going to bring the table up here, and we'll show you how to use it, but just keep in mind we're going to look for 9 degrees of freedom in the 95% confidence interval. So here is the table we've got. This is in your book, Appendix 2. It's on page A24, and it's a student's t table. And for right now, what we need to pay attention to is degrees of freedom down here, and then confidence interval over here, confidence level here. So one tail area and two tail area we don't need for now. What we need is degrees of freedom here and your confidence level here. So for us, we need 9 degrees of freedom. So we've got 9 degrees of freedom. So we go across 9 degrees of freedom, and we look for a 95% confidence level, which is right here. So we see where these cross, 0.95, we come down, see where it crosses with 9 degrees of freedom, and it's right here. So the t-score we need, our critical value, is 2.262. Okay, so we've got 2.262. So what we just did right here, this is like when we found the t-scores, but with when we found the z-scores, but it was much simpler because we didn't have degrees of freedom. So we just had that little box in your inside front cover that we used, and it was a little simpler. Now this student's t table, also most of you have all the tables in the inside front cover also, so you don't necessarily have to go in the appendix. It's probably right in the inside front cover where all the tables are. So to use it on your calculator to find this t-score, well, so here's the table, and then the calculator, it only is on the TI-84. It's not on TI-83, and it's not on all TI-84s. It was only on the TI-84 where the software on your calculator has to be from after January 2011. So if it's on there, then you can use this command called inverse t, and it works just like inverse norm. We plug in the area. The only difference is we have degrees of freedom. Okay, so it works like inverse norm. You plug in the area, it's going to give us a t-score, but it starts from the left. Just like before, it's going to start from the far left and go to a certain area. And we will actually look so we can see the area under the curve, because the student's t, remember, it's a different distribution, but it is very similar to the standard normal distribution. So the curves look kind of close. So if you have it in your calculator, the way you'll know is you go to the second button, go to second, and then vars. So go to second button, then vars, because that gets us to the distributions, and then this screen should come up. So if you have it, you'll see this. Now a lot of calculators won't have inverse t. They'll go right from inverse norm to this t PDF. So if you do have inverse t, then you use it just like this, and you can type in, how we would do it is we would go inverse t, and the area here, well, it's going to be kind of that same thing before. So to make this work, let me move this, let's see, move this over a little bit. So to make it work, I'll draw this student's t. Now we're going to talk about this a little bit more later, but basically student's t is sort of like standard normal, but it's a little bit thicker in the tail, so it doesn't come down as quickly to the horizontal asymptote. So it just kind of does something like this a little bit. So to use a calculator, just like when you use inverse norm, we have to think of the same thing. So we are going to have 95% of the curve in here, which means that we have 5% left over, which we cut in half, which gives us 0.025. And that will go here and here, 0.025, 0.025. So if we're going to use this on the calculator, we've got to type in the area starting from the left. So we go 0.025. And then degrees of freedom would be 9. And if you do this on the calculator, if you have that software, it'll give you negative 2.262. So it's giving us this t-score over here, which is a negative. Now when we actually use this number, we want to always use a positive. So you want to ignore that. This is another reason why it's easier just to use the table. The table is easier because you don't have to worry about this negative, because when we actually use this t-score, we need just the positive value of it like we got from the table. So if I find this t value here, it's going to be negative because it's below. We'll see that a t-score has a 0 here also, just like a z-score. So there's negatives over here, positives over here. So if you use a calculator, number one, it's a little more difficult because you have to think about this, because it's going to start from the left. So you have to, take the 0.95, the remainder 0.05 cut in half to get a 0.025. So it's a lot more work, and then you always have to remember to not use the negative. Ignore the negative always. So if you're using the calculator, there's just more to remember. So that's supposed to say ignore. So it might be just easier to use, that actually is easier just to use the table. But if you want to use a calculator, that's how you would do it. So we should probably take a look at this student's t distribution. And you can see once again the software doesn't seem to want to work nicely together. So we've got this big gap here, but on your printout, you should not see this big gap. So I will try to make this work here. So we're going to look at the plot of the student's t distribution. So student's t, I'm going to start off with the standard normal curve. So this is a plot of the standard normal curve, and then I'll compare it to student's t. So here's standard normal. This is what we've seen a whole lot of times before, so we're familiar with this one, standard normal curve. And with the standard normal curve, we've got a 0 here. And let's see, so this is our standard normal. And what we're going to do is draw student's t underneath here so you can kind of see what it looks like, because they're kind of similar. So we know that when we have standard normal, we have z equals 0. Well, here's the new thing. When we have student's t, we're going to have t equals 0. So there's still, student's t has a 0 here too. And then depending on degrees of freedom, the graph will look a little bit different. So let's say you have something like 3 degrees of freedom, and then student's t would go something like this. So see how there's more area underneath the tails? There's more probability out here where student's t cuts to the horizontal axis quickly. Well, or sorry, standard normal cuts to it pretty quickly. Student's t is not so much. There's more probability out here in the tails. So this one would be like maybe 3 degrees of freedom. Now, if you have 6 degrees of freedom, it approaches the standard normal. It's a little bit more like the standard normal. So it goes something more like this. So this one is 6 degrees of freedom. And what we'll notice is that as you get higher and higher in degrees of freedom, more and more degrees of freedom, student's t, this student's t curve will approach the standard normal curve, so that at an infinite degree of freedom, you'll have the student's t will become the standard normal curve. So there's a couple of notes here we need. There's 2 of them here. One of the notes is, I guess I can put it up here, the area under the curve equals 1. Same as always, area under the curve equals 1. And the other note is what we talked about, there's more weight in the tails. So the probabilities go out to the tails more. And then as we mentioned here, as the degrees of freedom increase, the t distribution approaches the standard normal distribution. Just to see that, this you can sort of see here's degrees of freedom. So I'm back to that student's t table. Degrees of freedom as it goes higher and higher and higher. Look over here for infinity, and you should recognize some of these numbers, like this one right here should look familiar. This one right here, which we always use 2.58, and this one right here. And if you look above, these refer to 90, a 90% confidence interval, 95% confidence interval or confidence level, and a 99% confidence level. So when you have infinite degrees of freedom, student's t becomes the standard normal curve. Okay, so got a couple examples here. Before the example, though, let me just mention something about this degrees of freedom. So here's a quick example. Sometimes students say, what does that mean, degrees of freedom? You can kind of think of it as the number of variables that are free to change. So as an example of that, let's say you want, here's just an example. Let's say you want 80%, you want 80% average on 4 tests. Okay, so you're shooting for 80% average. You've got your tests here. Well, test 1, for the most part, can be any score, right? So you could get a 75 on test 1. It's okay. You can still get an 80 average, right? So then test 2 comes along. Pretty much it can be anything also, within reason. So maybe it's a 90. Maybe it's a 80. It doesn't really matter. It's free to change. It's free to be almost anything. Test 3, Same thing. Let's say you take test 3 and you get an 85. Well, at this point, if you want exactly an 80, there's only one score that will work. Test 4 has no freedom to change. It's going to have to be a 70. It's going to have to be a 70 to make this 80 average. So the way this is set up, we really had 3 degrees of freedom. And here we have 4 tests. So you can sort of see that n minus 1 even right here. That's just kind of an example. Degrees of freedom gives you the number of variables free to change. And it's not exactly a perfect example, but it gives you an idea of what we're talking about. So we've got a little box here. Let's get this out of here a second. So confidence interval for mu when sigma is unknown. So remember, this is the more likely case when sigma is unknown. And we're looking for a confidence interval for the mean mu. And we've got this formula here that looks exactly the same as what we saw in 7.1 because it is. The only difference is how we find E. So now, where before we had a z-score and sigma, now we have a t-score and little s. But other than that, they're very similar. So the little note here is just one difference, I guess, is that for this, we need to consider confidence level C, which we did before. Here's the difference, and degrees of freedom. Okay, so we didn't need to consider degrees of freedom before with standard normal, but with students T we do. Just remember degrees of freedom is just n minus 1, where n is the sample size. So I know by now you guys are probably super excited about trying a problem. So we've got example 2 here. And I just noticed we had just enough room to write something in here. A little extra space, always good to keep in mind. And you're going to want to write, I love statistics, so we don't waste any space here. And you could even do this. Who remembers what that means? Sometimes my students tell me they've never seen that before, and I don't know if they're telling the truth. When you're in 3rd grade, at the end of every love letter, don't you put TLA, true love always? Right? You guys know that one, right? True love always? If not, we're going to bring it back. Start putting it on the end of all your love letters. TLA, true love always. Get that thing started again. Okay, this should maybe help out with our love for statistics. Example 2, page 382, number 12. So page 382, number 12 says a random sample size of 81 has sample mean 20 and sample standard deviation 3. So part A says check the requirements. Is it appropriate to use students' t distribution to compute a confidence interval for the population mean mu? Explain. Well, we can say yes. The central limit theorem, right, CLT, says the X bar distribution will be approximately normal since what? How do I know this for sure? Because notice it doesn't say that we're sampling from a normal distribution, but it does say sample size of 81, right? N equals 81, which is greater than or equal to 30. So this is the same as before. 7.2 and 7.1 are the same here. So we're going to take these samples, right? We're taking these samples out of here. If we line up our samples on a number line, we need to make sure that they're going to line up in a nice bell-shaped curve, or in other words, be approximately normal. And in this case, we will, because our sample size is 81. And Then we can also say this. One more thing that's a little different here is this. Since sigma is unknown, since it's unknown, we use students t. We use students t, right? We can't use standard normal. If we know sigma, we can use standard normal. If we don't know sigma, we use students t. And then remember what we're going to do. We're going to approximate sigma with little s, the mean from the standard deviation from the sample. So part B says find a 95% confidence interval for the mean mu. Well, okay, we've got our formula. X bar minus E is less than the population mean, which is less than X bar plus E. To figure out E, we have our new formula, which is just a modification of the formula from 7.1. But now, of course, we're going to have a t-score and little s. So we have to figure out this t-score. Now remember, to find the z-score, we had that little table in the inside front cover of the book. It's much easier because we didn't have all these different degrees of freedom. So now to find the t-score, the hard way is actually to use the calculator if you have inverse t, but the easier way is just to use the table. So we need to figure out degrees of freedom. So make a little note here, degrees of freedom, it's equal to n minus 1, which is equal to 81, right, minus 1. So it's going to be equal to 80 degrees of freedom. So then we have to look at the t-score. We have to find the t-score. So we're going to look on that table. Look down to the 80 degrees of freedom and look across to a 95% confidence interval. So we need to know that. They want a 95% confidence interval. I'm going to write that down too. So we want a 95% confidence interval. So we need to use this and that on the student's t-table. So go ahead and take a look on the table, and hopefully you're going to find this. I'm hoping that when you look at the table, you're going to see t equals 1.990. So once we have that, we can start to build our maximal margin of error E. So we can say that E is equal to 1.990, and it said that in the problem it says that sample size of 81 has a sample mean 20 and a sample standard deviation of 3. So they told us that S was 3. In the problem, they told us S was 3 and that the sample mean was 20. Okay, so for N is 81. So this goes under here. So look what I'm doing. I'm using this formula. And there's a really easy mistake to make. It happens all the time. Look at the formula. It says N, right? N is 81. An easy mistake to make is to put an 80 here. That's degrees of freedom, right? Every time you use students T, you're always doing this N minus 1 thing. And a lot of times it's easy, if you go too fast, to just put this 80 for N, but that's not it. N is the sample size. The sample size is 81, so that's what goes here. Right? We use the degrees of freedom to find this t-score, but this is N, just like the formula says, little s over the square root of N. They gave us little s. So then if you go through here, it's 1.990. Of course, the square root of 81 is just 9. So really this is just 1/3. But if you go through the arithmetic here, you get right around 0.663. So this is our maximal margin of error, 0.663. So you can go back to the formula here. This is the same formula that we saw in 7.1. So once we have that, we can just fill in the blanks here. Basically fill in these blanks. So we are going to get, let's see, so x bar is 20. So we have 20 minus, I'm just going to round this to 2 decimal places, less than mu, which is less than 20, plus 0.66. So we get 19.34 is less than mu, which is less than 20.66. So this is what we get for our confidence interval. Now the book, again, they say it a little bit differently. So they say this, which is fine. As I mentioned before, I like this way better because it tells us what we're trying to approximate, the population mean mu. So then let's see, what else do they want? Part C, they want an interpretation. Explain the meaning of the confidence interval you have computed. Well, so for part C, we're just basically saying we're interpreting what we just found. So we can say this for part C. I just put it here. We are 95% confident and we can pretty much start all of these in chapter 7 the same way. We can always start with this. Another way this is stated a lot of times is there is a 95% chance. But I'm going to say it the same way every time just for consistency, so it makes it easier to learn and easier to remember. We are 95% confident. And remember, this is a mathematical statement. This speaks to the method that we're using that will give us an interval that is correct 95 out of 100 times. So remember, it's not a figure of speech. There's a mathematical meaning in this statement right here. We are 95% confident means that the process that we used will give us a true statement 95 out of 100 times. It doesn't mean we know we're right? This could be one of those 5 times that it's wrong, but we're 95% confident that this interval that we came up with is one that actually contains the population mean mu. So we say we are 95% confident that this interval and I've just been writing it in here to make it really clear. This interval right here, the one we just found, we're 95% confident that this interval is one that contains the population mean mu. Now, if this were a problem where we knew what mu represented, we would keep going here. We would mention what mu is. But in this case, we don't know what it is, so we can just leave it at that. Then we've got another example here, example 3, and this is just to check, okay? So again, this one is only to check. We have to build these from scratch by hand, but for checking, I'll just show you how you can do it on the calculator. So from the calculator, we go to the stat button, and then we go to tests. This is going to be very similar to what we did in 7.1, but this time we go down, and most calculators is number 8, but we go to what it says, T interval. Okay, because it is a confidence interval and we're using t-scores. So make sure you go to t-interval, not t-test, t-interval. So if you go to your calculator and hit the stat button and scroll over to tests and then go to t-interval, which on most of them it's number 8, and then it's going to ask you from t-interval, just like before, it has a couple of categories here. For the input could be data or the input could be stats. So in this case, we don't have the actual data. If we had the actual data, we could put it in a list, and then it would just look in that list. But we have the stats, so we just fill in the blanks. We tell it, if you're looking at your calculator, we tell it that the mean x bar is 20, the standard deviation, little s is 3, n is 81. We tell it the confidence level is 0.95. We ask it to calculate, and it's not very fun. It's not fun at all. It does all the work for us, and it gets the same thing we got. So you can always check confidence intervals on your calculator. Just remember that we have to build them from scratch, so we have to go through the process that we just did. But you can check them on the calculator also. And then finally, we've got another example here. It's on page 383, number 16. And when you are working on that, on page 383, they mention something in the directions. Right at the very top of 383, it says, in problems 13 to 19, assume that the population of x values has an approximately normal distribution. Okay, so we know that. So in other words, sample size is not going to matter. Some of these are going to have small samples, but it mentions that we're sampling from a normal distribution. And it talks about owning our own candy store. And it gives us a random sample of startup costs. Now these are in thousands of dollars. For a random sample of candy stores, we've got, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 candy stores. So number 16, we have got n equals 9. So when you look at part A, it says use a calculator with mean and sample standard deviation keys to verify that the mean is about 106.9. This is in thousands of dollars. And little s equals about $29.4 thousand. Now on a test or a quiz, I won't tell you that. I want you to find it. So just remember what we did at the beginning of the semester. We would put all the data in list 1, right? So just to recall, here's what we did before. We put the data in list 1. In list 1. And do you remember what command we would use to get basic statistics? We did it all the time. We would use one variable stats, right? So to get this information right here, I wouldn't give it to you. I'd give you the data, and then you just have to put it in a list, do one variable stats, and then one variable stats will give you this, right? So we know that we're looking at a sample, so we're not going to use sigma here, right? There's only 9 candy stores. The setup cost for 9 candy stores. We know there's more than 9 candy stores in the country, so this is a sample, and it tells us it's a random sample of candy stores. So we know we need little s, sample standard deviation. So we get both of these off of one variable stats. And then they want us to find a 90% confidence interval for the population average startup cost for candy store franchises. Okay, so for this one, if you look on your Chapter 7 handout for the formula, you've got our familiar formula, x bar minus e is less than mu, which is less than x bar plus e. We need to find e, right? So this is all from the Chapter 7 handout. And what we really need to do is find t sub c. This is the one that we need to find first, is t sub c. And we do that by knowing that we've got, they want a 90% confidence interval. So, yep, so for part B, this is finding 90% confidence interval. So we know we've got 90% confidence interval. We need to know degrees of freedom. Well, there are 9 pieces of data, right? They gave us 9 pieces of data there. So we've got 8 degrees of freedom. Remember, degrees of freedom is n minus 1. N minus 1, which is 9 minus 1, which is 8 degrees of freedom. So what we need to do is go to the student's T table, because we're looking for this, and look under 90% confidence interval and 8 degrees of freedom. So 8 degrees of freedom, that'll be down the side, and then we can find the confidence interval. So we've got it right here. So to look at this, we've got 8 degrees of freedom. 8 degrees of freedom, we want a 90% confidence interval. 90% confidence level, 8 degrees of freedom. It looks like it is 1.860 is our t-score. 1.860. So let's see, we've got 1.860. So we can build E now to see what we've got. So E equals 1.860 and little s, 29.4, the square root of n. Remember, what's an easy mistake to make here? Don't put that, right? Put n. N is 9, so plug a 9 in here. And if you go through the arithmetic here, you should get about 18.2. So then we can build this thing. We can use this formula here. So x bar is 106.9 minus 18.2 is less than mu, which is less than 106.9 plus 18.2. And that gives us, let's see, it gives us 88.7 and 125.1. Remember, this is the Greek symbol for mu, for the population mean. So really what this means is this is in terms of thousands of dollars, right? This is $88.7 thousand, $125.1 thousand. We think that the population mean startup costs for these franchises is somewhere in between here, right? Not necessarily right in the middle. It might have just barely caught it. It might be 88.9. Could have even missed it. But 90 times out of 100, we'll get a true statement and where the population mean is somewhere in between these numbers, right? Don't think it's like right in the middle. Where we are, the middle of these two numbers is our mean, right? We're building this around this sample mean of 106.9. So this is our confidence interval. This is our 90% confidence interval right here. And then for part C, it says, what does confidence interval mean in the context of this problem? And this is the part we always struggle with. We struggle with this part a lot. So for part C, remember what we can always say initially. You can always say we are 95% confident. Oops, not 95%. Erase that. This one is 90%. So we are 90% confident that this interval, so every single one of these we can start the same way. And again, these are in thousands of dollars, that this interval is one that contains, and it's a population mean, but in this case we can say what it is. And the easiest way to do the wording is I look at the question. If you look at that question on part B, it says, find a 90% confidence interval for the population average startup cost mu for candy store franchises. I'm just going to use their same wording. Contains the population average startup cost costs mu for candy store franchises. So a lot of times the easiest way to figure out what to say here is just use what the book says, what the book's question is. But look what's the same every time. We are 90% confident that this interval is one that contains, And basically we're going to say mu, right? We're going to say mu, but in the wording of the problem. So there's some consistencies here. So, if you use those consistencies, a lot of times it makes it easier to understand how the problems work. So hopefully that'll give you guys enough to get started. So give them a try. 7.1 and 7.2 are similar. Just remember 7.2 we have to use student's T because we're not going to know sigma. And give them a shot and let me know if you have any questions.